Now we are discussing about the most powerful class of automata, namely Turing machines. We learned about Turing machines, their applications as language acceptors and transducers, and in the last class we have seen different variants of Turing machines, and we observed that when we are adding more structural components to a standard Turing machine, we are not getting more powerful machines. And today we are going to look at what is called a Universal Turing Machine. It is like a general purpose computing device like a digital computer. If you look at a digital computer and suppose you want to check primality, that means you want to check whether a given natural number is prime or not. So what you do is you will supply a program to check primality and an input to that program, that is a program P, and an input, that is a number to the program P, will be given to the computer, and the computer will run the program P on the input number and will tell whether the given number is prime or not. Similar to that, today we are going to discuss about a machine, that is a Turing machine, which will take another Turing machine M and an input to the given Turing machine, and will run that given Turing machine on its input and will produce the output for that Turing machine. Just like the computer which takes a program to check whether a number is prime or not, what the computer is doing is it takes a program P and an input to P, and it runs P on the input and produces the result of P on its input. Similar in nature, today we are going to see a Turing machine, say U, which is called a Universal Turing Machine, which takes another Turing machine in place of primality checking program. Here it is going to check another Turing machine M like a program, and it will take an input to M, and what it is going to do is the Universal Turing Machine will run the other Turing machine M on M's input and will produce the output of running the Turing machine M on its input. So this is what we are going to discuss today, and we are going to see in detail what is the Universal Turing Machine and what is the importance of this machine. And before we see what is it, let us recollect unary encoding that we discussed for a set. We can recollect it using an example or a sequence of examples. Suppose you have a set and you want to find a unary representation of the elements of that set on the singleton alphabet 1. For example, suppose you have a set of states like capital Q with the M states in it from Q1 to Qm. We know the unary representation of Q1 is 1, Q2 is 1 raised to 2, that is 2 1s. Likewise it goes, and Qm is represented by 1 to the power m, that is a string of 1s with a length m. So the first element is represented using 1, second element using 1 1, third element using 1 1 1, likewise it goes. Another example, suppose you want to represent the alphabets in the input alphabet of an automaton in unary, then here again the first alphabet will be represented as 1, second alphabet will be represented as 1 1, etc. It goes up to 1 to the power k if there are k alphabets. And one more example, suppose you want to see a unary representation of the directions in the direction set, that is left and right, you can represent it using 1 and 1 square. So 1 represents left, 1 1 represents right. So what we did is we have found a unary representation for the elements of a finite set. As an example, now suppose you were given with a unary representation 1 1 or 1 square. You can say that it represents the state Q2 if it is representing a state. So if it is representing a state, it is 1 1, that is the second state and is Q2. And suppose it is representing an alphabet, then it is A2, it is the second alphabet. 1 1 means the second element on that set. So it will be the second alphabet, in this case it is A2. And if it is representing a direction, what it can be? The second direction, which is right. So it will be representing capital R if it is a direction. So what we show is that a given unary string is representing one of the elements depending on the context in which that particular representation appears. Suppose it appears in a place where you need a state, it is Q2. Suppose it appears in a context where you need an alphabet, then it is going to represent A2. And if you are having this representation in a context where you expect a direction, then it is the right direction. So you can have a unary representation for representing the elements of a finite set. And if you have this singleton alphabet set, then the ith element of that set can be represented by a string of ones with the length I. That is 1 to the power I. The ith element is represented as 1 to the power I, a string of ones with the length I. So the first element of the set will be represented as 1, second element as 1 1, third element as 1 1 1, etc. So a unary string 1 to the power 4 will be representing the fourth element of the concerned set. If you know which set it is representing, then you can identify what that element is. So that is a unary representation. And with this, now we can try to look at the definition of the Turing machine that we have learned. Please don't get confused about it. We can discuss it with an example. So this is the coupled definition of a Turing machine, where the first element is a set of states. For example, suppose you have 5 states, Q1, Q2, etc., Q5. Second element is the input alphabet set, and assume you have 3 input alphabets, A1, A2, and A3. And thirdly, you have the tape alphabet, and now suppose you have 5 tape alphabets, A1 to A5. And note that the tape alphabet is going to be a superset of the input alphabet, because the input string needs to be stored in the tape, and hence every input alphabet must be a tape alphabet. And without loss of generality, assume that the first sequence is the input alphabet followed by the remaining alphabet on the tape alphabet set. And the fourth component is the start state, which is a state, and in this case Q1. And next is the transition function. There can be a number of transitions like this. Now you are saying if you are in state Q1 and if the current input symbol is A2, then you change your state to Q3, replace the alphabet A2 on the tape with A1, and you move your read write head to the right. Similarly, you can have a finite number of transitions. And the next example is the Luston marker, and which is the simple A4 on the alphabet set. The tape alphabet must contain a left-hand marker. Suppose it is this simple. And next is the blank symbol on the tape, and let us say it is the last symbol here. It is nothing but the blank symbol. And the next component is the accept state, one of the states, say Q4, which is an accept state, which is the accept state, and finally the reject state, that again is a state on the state set. So this is an example Turing machine, and these are the structural components defining a Turing machine. And now we can see how will you apply the unary encoding to the elements of a Turing machine. And this is the example that we discussed. And now, how will you represent all these states in unary? The first state will be represented as 1, second state will be represented as 1, 1. Likewise, you can have a unary encoding, and here is the unary encoding for all the 5 states, 1, 1, 1, etc. up to 5, 1. This is what we already discussed, just apply it. Similarly, for the alphabet set, you have these 3 unary representations for A1, A2, and A3. The third alphabet, whatever it is, represented by 3 ones. Similarly, for the tape alphabet, you have this set. Now, what is the start state? It is Q1, which is the first state, so you are representing it with 1, meaning the first state, which is Q1, is going to be the start state. Now, what is the transition relation? Here you can say that from the first state, that is Q1, if you are getting the second alphabet, that is A2, then you change your state to the third state, which is Q3, and you replace the second alphabet with the first alphabet, that is A1, and then you move to the right. This is exactly this. So this is a reversible transformation into unary, a one-to-one correspondence, easy to translate and get it back. And now you are saying the left-hand marker is the 4th alphabet, that is 4 ones means the 4th alphabet here. And the blank symbol is the 5th alphabet here. And now the exit state is the 4th state. What is the 4th state? Q4. And now finally you are saying the reject state is the 5th state in the state set, that is Q5. That's right. So this is a unary representation of the elements of the sets defining a Turing machine. And with this, we can define a unary encoding of the machine, and note that the name of an element in a set is irrelevant. For example, here you can see that these 2 encodings are same, 1, 1, 1, 3 1, 4 1, and 5 1. So the state element is having a name that doesn't matter. So 1 represents the first element. If it is a state, it is Q1, and if it is an alphabet, it is A1. And that's it. So the state name is irrelevant, and hence to represent it, it is enough to just know the number of elements in the state set. If you know that it is 5, then you know that the states are going to be represented as 1, 1, 1, 1, 1, 1, then 4 ones and 5 ones. That's it. So no need to, in fact, know the names of the states. Just the number of states is enough. Then you know that the unary encoding is this. This represents the first state, and a string of I ones represents the ith state. So the name is irrelevant. And with this, now we can proceed and we can try to formulate a binary encoding of a Turing machine as a whole. So far, we have encoded the components of a Turing machine in unary, and now we are going to combine it to have a single binary string representing a Turing machine. So you consider the same example. The only difference that I made is that I moved the definition of the transition function to the last, and that is the only difference. It's exactly the same. And now we need to formulate a binary encoding for this Turing machine, and accordingly we can generalize the representation. So I am giving you a binary representation for this. Please don't get worried about the long binary string. I am going to explain it, what it is. And first is saying how many states are there in Q. How many are there? 5. So 1 to the power 5 says there are 5 states, and that is enough. Then it says the states are going to be represented as 1, 1, 1, 3 ones, 4 ones, and 5 ones. So just the number of elements of a set is enough. So that is the first component, and the successive components are separated with a 0, and that is the use of 0. The only use of 0 is to delimit 2 components in the definition. So there are 5 states, then there are 3 alphabets in the input alphabet set. The first, second, and third represented as 1, 1, 1, and 1, 1, 1. And now the third component says there are 5 alphabets on the tape alphabet set, and not that all these 3 must be there. So it must be greater than or equal to 3. And next, the fourth is the start state, that it tells you that the first state here is going to be the start state. That's right. The next is the lesson marker. It says that the fourth alphabet on the tape alphabet, that is A4, is going to be the lesson marker. Then proceed. It says the fifth tape alphabet, that is A5, is going to be the blank symbol. Then it says the fourth state on the state set, which is Q4, is going to be the accept state. And next says the fifth state on the state set, which is Q5, is going to be the reject state. So the first 8 components, string of 1 separated by zeros, are representing the first 8 components. And now what remains to be addressed is the representation of the sequence of transition functions. Now we have 2. And the next is the first transition function representation. It says if you are in the first state, that is Q1, and if you are reading the second alphabet, that is A2, and then what do? You change your state to the third state, that is Q3, and you replace the second alphabet A2 with the first alphabet A1, A2 with A1, and you change your tape head to the next symbol on the right, because 1, 1 represents right, and this is what you are saying. The second direction is right. So this is how you can represent a transition relation. 5 representations are there for the components, and they are separated with a 0. And the next transition, that is if you are in the second state, and if you are reading the third alphabet, you change your state to the fourth state, you replace the third alphabet with the fifth alphabet, A3 with A5, and you move to the left. So that is a binary encoding of a Turing machine. So it's very easy and very straightforward. First you encode all the components in unary, each of these elements, and now 2 components are separated with a 0, and it is clear that no need to remember the names of the state, just the number of states is enough. That is 1 to the power 5 means 5 states. Then the states are going to be represented as 1, 1, 1, etc. up to 1 to the power 5. So this is a binary encoding, and now we can generalize and formulate it as a lemma, saying for any Turing machine M, there exists a unique binary encoding hat M. So hat M in this lecture is going to represent a binary encoding of the Turing machine M. I hope you are getting it, and now proceed and see a binary encoding for an input string. And suppose you have this input alphabet set AB, and you know that using unary encoding with the alphabet set 1, A can be represented as 1 and B can be represented as 1, 1, the first alphabet and the second alphabet. Then we can apply a very similar concept to encode a string. Suppose you have a string W on the alphabet set sigma, then it can be represented in binaries, which is denoted as hat W, that is the binary encoding of W is hat W, such that the alphabets in W are encoded in unary And in this string, the unary representations of the characters are separated with a 0. Look at examples to understand what it is. So this is your input string, then how will you represent it in binary? So 1 is represented as, the first alphabet followed by the second alphabet, that is 1 1, followed by the first alphabet, followed by the second alphabet. It's very easy to encode and decode. If you decode, it is A, B, A, B, because the first alphabet, second alphabet, first alphabet, second alphabet. So unary encoding for each alphabet, and the successive alphabets are separated with a 0. Second example, BAB. So it's going to be 11011. Sorry, 11011011, because an A is there in between. And third example is BAAB. So what would be the hat W3? That is a binary encoding. It should be 110 followed by 1, that is A, followed by 0, followed by 1 means again A, followed by 0, followed by 1 means B. So that is the binary encoding, and that is again a very straightforward way of encoding an input string in binary. And with this we can have a lemma saying for any input string W to a Turing machine M, there exists a unique binary encoding hat W. So remember, if you have a Turing machine M, you can have a unique binary encoding hat M representing the Turing machine. And if that Turing machine is going to take W as an input, then you can also have a binary encoding for W, namely hat W. And now we can look at what is called a universal Turing machine. So this is the diagrammatic representation of a universal Turing machine U. It is going to take a string as input as always, the Turing machine or any other automata do. So it takes a string as input, and what is the string? It is an encoding of a Turing machine M and an encoding of an input W to M, separated with a simple hash. Not that this is going to be a binary encoding of the Turing machine M, and hat W is nothing but a binary encoding of the input W to the Turing machine, and these two binary encodings are separated by the simple hash, and that is the input to a universal Turing machine. So just like we give a program to check primality and a number as input to a computer, here we are giving a Turing machine encoding and an input to the Turing machine, not directly the input, the encoding of the Turing machine as input to a universal Turing machine, and what are the possible outcomes. And what the universal Turing machine is going to do is, just like the computer which runs the primality testing program on the input, it is going to run M on W and accepts, the universal Turing machine accepts the input if the Turing machine M accepts W, and the universal Turing machine rejects its input if M rejects W. So what the universal Turing machine is doing is, it is running the given Turing machine on its input W and accepts if this Turing machine accepts W and rejects if M rejects W. And I hope you are getting it. Otherwise, please watch it again and see what the Turing machine, universal Turing machine is doing. So what is the input? Input is the binary encoding of a Turing machine. This is exactly the same example that we discussed, the encoding of a Turing machine and the encoding of an input string. If AB is the alphabet, the input string is AB, AB, because the first alphabet, second alphabet, first alphabet, second alphabet. So the encoding of a Turing machine, that is hat M, has the encoding of an input string W, that is has hat W, is given as input. then what the Universal Turing Machine is doing? The Universal Turing Machine U takes as input the binary encoding hat M of a Turing Machine M and the binary encoding hat W of an input W to M. And these two are separated by a hash. So if you look at the alphabet set, input alphabet of U, this is a binary string and this is again a binary string, and they are separated with a hash. So the input alphabet set sigma for U is going to be 0, 1 and hash. These two encode both M and W, and they are separated with a hash. Now given an input string, hat M has hat W, that is the encoding of Turing Machine M, hash encoding of input W. What it is doing is, it checks whether the first encoding is a valid Turing Machine encoding and the second encoding is a valid string encoding. It checks for the validity. It may not be representing a valid Turing Machine, or it may not, the second one may not be representing a valid input string. If that is the case, then the Universal Turing Machine immediately rejects, and that is what it is doing. Now the question is, how is it that the Turing Machine can check whether the first binary string is a valid encoding of a Turing Machine? In fact, you can have a finite state automata for checking the validity like this. A finite state automaton to check the validity of whether the binary encoding is representing a Turing Machine or not. You know that it should be represented by the number of states. So a sequence of one or more ones is detected by this part of the finite state automaton, then a 0. After that, the number of input alphabets, one or more, followed by the number of state alphabets, then followed by the start state, then followed by the left hand marker represented by a sequence of one or more ones, followed by the right hand marker, the blank symbol, that again is a string of ones with one or more ones in it, then followed by the accept state, again a sequence of one or more ones, followed by the reject state, that again is a sequence of one or more ones. Then a sequence of transition functions, that is why I am having a bracket, then a sequence of 5 unary strings of ones are processed. And not that in this encoding, it allows to accept a Turing Machine as valid even if there are no transition functions. If you want to have at least one transition function, you can easily modify it. And I hope you are getting it. So the Turing Machine is empowered to see whether the encoding is valid or not. Similarly, you can have another Turing Machine which is just a finite state automaton to check whether the second encoding is a valid string encoding or not. You say that the first alphabet represented by a sequence of one or more ones, followed by 0, then the second alphabet again a sequence of 1, then 0, again a sequence of 1, so it can have any number of finitely many alphabets. So you can easily verify it. Thus, the Universal Turing Machine first checks whether these are valid encodings of a Turing Machine and an input. If it is not, then it immediately rejects and returns. And suppose these are valid encodings, then what Universal Turing Machine is going to do is, it runs the Turing Machine M on W. It should be M and W. Sorry for the typing mistake. It should be M on W, not the encoding on the encoding. What it is going to do is, it is going to run the original machine M, not hat M, on the input W and not on hat W. Sorry for the typing mistakes, I will change it. And what it is doing is, it accepts if M accepts W. So it is just running M on W, and if M is accepting W, then the Turing Machine blindly accepts. And if M is rejecting W, then the Turing Machine U also just rejects its input. That is, this is its input. And if you remember, there is a third possibility, that is, it is neither accepting nor rejecting. That means it is looping. That is, if the Turing machine M is looping on W, then the universal Turing machine is also going to loop. And that is the outcome of the universal Turing machine. So what would be the language? You can see that the language of the universal Turing machine is the set of all Turing machine encodings followed by an input to that Turing machine such that W is in the language of M. And suppose that W is in the language of M. And why is it that W is in the language of M? Because the Turing machine M accepts W. Then by definition, the universal Turing machine is accepting. Now suppose M is rejecting W, then the Turing machine is rejecting. That is, the universal Turing machine will reject its input. So that may not be there. And suppose M is looping, even in that case, because the universal Turing machine is looping, U will not accept. So this is precisely the language of the universal Turing machine, which is the set of all Turing machines M and an input W such that M accepts W. And not that the input is encoding of M followed by a hash followed by encoding of W. And on this slide we need two changes. This should be M and this should be W. And sorry for this hash symbol, I will change it. And that's it. And now proceed and see the structure of a universal Turing machine and also see how exactly it is working. So this is going to be the structure of a universal Turing machine. This is a typical structure that I am presenting. So what are its components? There is a finite state control unit for the universal Turing machine U. And there are three tapes. The first tape is storing the encoding hat M of the input Turing machine M. And the second tape is going to store the encoding hat W of the input W. So the input is stored in two tapes. The encoding of the Turing machine in the first tape and the encoding of the input to M in the second tape. And what is the third tape? The third tape is storing the current state of M. So here it says that it is 3. That means the current state of M is the third state of M. And the current position of the tape head in M. It says that in the Turing machine M, its tape head is positioned to the second cell on the tape. So the tape head position is here after the 0, and before the 0 you have the current state of the Turing machine M. Not that it is the state of the Turing machine M. And the universal Turing machine state is here in the control unit. So these are the structural components, and now you can see how is it working. And what U is doing is, once after setting its input like this, it is repeatedly executing the following statement for what? To simulate a single step of execution of the Turing machine M on W. Not that M is in the encoded form and W is again in the encoded form. So to just perform a step of computation of M on W, U is going to repeatedly perform a sequence of operations. A sequence of 5 steps are required to execute a single step of M on W. And what is the first step? First step is scan tape 3, where you have the current state of M and the current position of the tape head. From here you know that it is Q3 and the tape head is to the second cell of the tape of M. And so you know that by scanning the third tape. The universal Turing machine always is pointing to the leftmost impulse, and in this step it scans this tape and finds the current state and current position of the read write head on the tape of M. Then by using that position, scan tape 2 and find the next input symbol. You know that the input to M is stored in the second tape now from here you know the position of that read head here, and you go to that position here and find what the next input symbol is. And third step, now you know the current state and current input symbol, and with this you go to the encoding of the Turing machine M and see what transition can be applied in the current configuration. I say the transition because I assume that M is a deterministic Turing machine. For example, suppose your current state that you are finding from here is Q3, and the next input symbol that is given by the second tape at cell 2 or the second alphabet is AI, suppose the ith alphabet. Then you need a transition when you are in Q3 and you are reading AI as input. Suppose it is given like this. You move your state to Q4, you replace AI with AJ, and you move to the right. This is the transition on M. Then how will you update? You want to make the state changes. Here you want to make it 4. Now it is 3. You want to make it 4. So you want to change the tape content here. Then you want to replace the symbol on the tape. That you have to do in the second tape. And finally you want to move the read head to the right. So here you will say that now the position of the read head is positioned to the next symbol. So accordingly you want to apply this transition and accordingly update the tapes 2 and 3 to reflect the step. That is, you want to update the state, you want to update the tape symbol, and you want to update the position of the tape head. And that is what you do. And if you do that, then suppose this machine is entering the accept state of M or reject state of M, then the Universal Turing Machine accordingly will enter the accept state of the Universal Turing Machine or the reject state of the Universal Turing Machine. Not that these are sync state. Once the machine gets into it, it will remain in that state forever. So these are the sequence of 5 steps that the Universal Turing Machine is doing to simulate a single step of the input Turing machine M on the input string W. And I hope you got it. Otherwise, please watch it again and try to understand exactly what is the structure of a Universal Turing machine and what it is taking as input and what it is performing and what it is generating as output. And with this, we are finishing this lecture and we are moving on to the last slide where I am giving you an exercise as assignment for you to practice and understand how can you obtain a binary encoding of a Turing machine. So you are given with a binary encoding, you are asked to decode it and produce the original Turing machine M, and that is the assignment. Today we discussed about what is called a Universal Turing Machine, which is like a general purpose computer. And the Universal Turing Machine is taking as input 2 binary strings separated by a hash. And the first binary string is going to be a binary encoding of an arbitrary Turing machine, and the second binary string is going to be the binary encoding of an arbitrary input to the input Turing machine. And what Universal Turing Machine is doing is it will simulate the input Turing machine on the input string and accepts if the input Turing machine is accepting its input, rejects if the input Turing machine is rejecting its inputs, and loops if the input Turing machine is looping on its input. Thank you.